Hello and welcome to my wet lab analysis presentation. So in the beginning I was assigned nitrate spectroscopy for my method and introduction. However, I have elected to analyze unknown solution A as I thought it had the most relevant and useful data to analyze. To kick things off, we're going to go over why it's important to measure and maintain nitrate levels in the soil and in water supplies. So one of the biggest uses of nitrate is in fertilizers. So this will be the form of potassium nitrate, most likely, and the issue arises when you have fertilizer runoff into local streams and rivers. So this buildup in nitrate in our water supplies can be both harmful for people in general and also for the environment. So for the environment, these increased nitrogen or nitrate levels allow for algae to grow and thrive, and as this algae is using up all of the oxygen in the water, it ends up suffocating all other life. So this is incredibly harmful for that environment as all of these different organisms aren't able to get enough oxygen. And then also in terms of us as individuals, these increased nitrate levels can cause formation of quite harmful compounds which can be carcinogenic and can cause birth defects and all sorts of horrible things. So in order to monitor these levels, we've got a few different techniques available to us that we can use to maintain and monitor them. So potentiometric analysis is a common method used. However, the problem with this is it can be quite uncertain and also it's quite expensive to decrease these errors. So we're going to be looking at chemical analysis of the water using salicylic acid and end up getting a calibration curve and then working out our concentration of nitrate that way. So I'm going to move on to the method next. So here's a general method for nitrate spectroscopy, but basically what you want to do is you want to make up a big stock solution of potassium nitrate at known concentration, and you also want to make up a 5% salicylic acid in H2SO4 solution as well. You will do a serial dilution of your potassium nitrate, and you'll add a little bit of this 5% salicylic acid to each one of them. You will then add 2 molar sodium hydroxide to ensure the pH is above 12, and at this point you should have a nice yellow color appearing. You will then measure the absorbance using UV-Vis of each of these different solutions, and from this you'll be able to plot a calibration curve of your absorbance to concentration, and then you will be able to do a similar thing again with your unknown water sample to find that's absorbance, and then you'll be able to compare that to the calibrated data that you found and work out what your concentration of nitrate is in your unknown solution. Unfortunately, we're going to have to throw all of that out of the window now, as I chose to analyse unknown solution A, which does not contain any nitrogen spectroscopy, so I hope that I'm going to be able to do this justice. So first thing we're going to look at is a general overview of how we find each and every ion in this solution. So a big thanks to Simon for making these beautiful diagrams. To begin with, we're going to look at group 1, which makes insoluble chlorides. After this, we will look for insoluble sulfides in high acidity. We will then look for insoluble sulfides in base. After that, insoluble carbonates. And finally, for group 5, there will be flame tests. And for NH4, we will look at pH paper. For group 1 cations, we're looking for insoluble chlorides. So 15 drops of 6 molar hydrochloric acid was added to 5 milliliters of the unknown solution and put in the centrifuge. The centrifugate was then kept to the side for further group tests, and our solid was washed with water and with hydrochloric acid again, put in the centrifuge, and this was repeated several times. When doing the test for lead, we found that no precipitate formed, and also for mercury again, no precipitate formed. However, when acidified with 6 molar HNO3, we had a nice white precipitate forming, and with the crystal of Ki, we had a kind of yellowy, creamy precipitate as well. So this is quite conclusive that we have silver in our unknown solution. So after finding that in our unknown solution we had a group 1 ion as silver, we moved straight on to looking for our group 2s. However, when testing for these, we found that no precipitates formed whatsoever. So we then started looking for insoluble sulfides in bases. Here is the analysis pathway for our group 3 cations. So when testing for our cobalt and our nickel, it was found that no precipitate formed whatsoever. However, when testing for our zinc, we ended up getting kind of a white crystalline structure / precipitate forming throughout the liquid. So that's a good indicator that we do have zinc in there of some kind. Apparently it should have come out as a kind of red precipitate, but I did read a few sources that mentioned that zinc ferrocyanide is in fact kind of a milky white colour, so that's something to bear in mind. Further testing for chromium and aluminium resulted in a colourless centrifugate, which rules out chromium, and no precipitate forming, which is our aluminium not being there. Further testing for iron resulted in getting a kind of lovely red precipitate forming, which indicates that we do in fact have our Fe3+ ion in the solution. So now we've identified 3 of our unknown ions, we've finally got to look at group 4 and group 5. So we're going to look for insoluble carbonates, and then we're going to be doing a few different things like flame testing and pH paper to find our group 5s. So finally we have our group 4 and 5 analysis pathway here. So first of all we're going to look at the insoluble carbonates. So when testing for barium we found that no precipitate formed at all. Same thing for calcium, nothing formed. However, for our magnesium we did end up getting a nice white precipitate forming, so we can definitely say that we have magnesium in there. When doing our flame test we found it was just a regular yellow flame, so there was no lithium or potassium or anything in there at all. And then when testing the pH paper on it, we found that the paper didn't change colour and there was no smell released, so there's no ammonium or anything in there either. So as an overview for all of the tests that we've just done, we can safely say that we have one group 1 ion, which is our silver, we have 2 group 3s, which is our zinc and our iron, and we have 1 group 4, which is our magnesium, and nothing else indicates that there are any other ions in there, so I think we can safely say that these are the 4 ions in this solution. So next is the calculation for working out the concentration of the iron ions in this solution. So this is a similar technique to what I discussed at the beginning with nitrate spectroscopy. However, for this it's iron spectroscopy. So it's the same thing where we have a big stock solution which is diluted several times. We work out the concentration of these dilutions and we record the absorbances. We then are able to plot this on a absorbent to concentration graph, which is our calibration curve. We then grab the equation of this line where y is our absorbance and x is our concentration. We can rearrange this to work out what our concentration is of our unknown, as we know what the absorbance is. And calculating it here, in this 50 milliliter dilution, we have 6.51 times 10 to the minus 5 moles per decimeter cubed. And then what we want to do is we want to work backwards to what the original 2 milliliters of the unknown solution was. So we want to do C1V1 equals C2V2, which I've rearranged here. So here is the equation for that, which ends up giving us a concentration in the original sample of 1.628 times 10 to the minus 3 moles per decimeter cubed. The next set of data recorded was with the ICP. So we want to be looking at unknown A here. And the first glaring thing that we can see is that we've already worked out we have 4 different ions in this solution. However, we only have 2 results. So we're missing data for our silver and for our magnesium. This could be due to many reasons. It could be that the concentration of these ions wasn't high enough for the machine to pick up, but I'm not entirely sure as to the sensitivity of this machine, so I'm not sure how good of a reason that is. Another thing is that it's quite new, so it's possible that the technique that was carried out was done incorrectly and it resulted in no data being recorded for these 2. However, we did end up getting data for iron and for zinc, so we'll make the most of it and we'll analyze these as best we can. This is currently in ppm, but for ease of access we want to really have it in molarity so we can compare it with previous data that we've collected for the iron. So I'm quickly going to go over a quick conversion of ppm to molarity. So ppm is milligrams per litre and molarity is moles per litre. So we want to go from milligrams to grams, so we divide by 1,000 to get grams per litre, and then we divide that by the atomic mass of whatever ion we're looking at, and that will end up getting us moles per litre, which is the same as molarity. So that's how you do that. So if we do this for iron, we get that our concentration at the end is 1.63 times 10 to the minus 3 molar, which is a good indicator as the previously worked out concentration with spectroscopy is very, very close to this. And then we also did it for zinc as well, and we ended up getting a concentration of 7.345 times 10 to the minus 2 molar. We haven't really got anything to compare this to, but we'll make do with what we have. So one thing to consider is the validity of this ICP data collected. So here we have all of the calibration curves for the ions that we were meant to have recorded. The first glaringly obvious thing, which has been eloquently put here as obviously naft, is the silver calibration curve. It's probably a good thing in the end that we didn't get any data for this one, as it would have been incredibly unreliable. So yeah, that one's unfortunate. Moving on for the iron, we have very nice line here which goes through the origin. We have a correlation coefficient of 0.9999, so I think it's quite safe to say that this one's been quite well calibrated, and the data we get for this one is pretty accurate. Not too bad, pretty reliable for that one. Moving on to zinc, however, we do see that there is a little bit of wonkiness going on here, shall we say. Our coefficient is 0.98, as we can see there, so there will be some uncertainty with this one as it wasn't quite calibrated correctly. So the molarity that we worked out previously for this one should be taken with a pinch of salt. It's still close enough to be pretty accurate on like roughly what the concentration is, but it's not perfectly accurate, I suppose. And finally, if we were looking at the magnesium curve here, this one is also quite well calibrated. So if we were able to get a result for this one, I think we could say that it was quite safe. We could quite safely say that it would have been quite accurate data for that one. So quickly, just before we wrap things up, I wanted to do a little comparison of the calculations for the concentration of iron. So for the UV-Vis spectroscopy, we got it as 1.629 times 10 to the minus 3 molar, and for ICP we got 1.630 times 10 to the minus 3 molar. So these concentrations are very close together with only a 0.001 difference. I think it's quite safe to say that this is the concentration of iron in the unknown solution. However, I'm more inclined to lead towards the ICP concentration, as it was calibrated quite nicely, and I'd hope that the machine was more accurate than me just calculating it on Excel. Yeah, so I think that pretty much wraps it up for the analysis of this unknown solution A. We found that it contains silver ions, zinc, iron, and magnesium. We calculated the concentration of iron in this solution to be 1.63 times 10 to the minus 3 molar, and due to how it was calibrated and this being our only source of data for the concentration of zinc, we're saying it's roughly 7.345 times 10 to the minus 2 molar. However, as I said earlier, that one should be taken with a pinch of salt. There is some uncertainties there, but that is pretty much what the concentration of that is. So I think that pretty much wraps everything up. Okay, so just before I give the final farewells, I'm going to go over the bibliography just in case you've forgotten where any of the citations were. So 1 to 4 were for my introduction and method section regarding nitrate spectroscopy, and 5 and 6 were just on papers I read about that seemed to mention that zinc ferrocyanide was in fact a white precipitate, like a milky white precipitate forming. So I don't think there's anything to worry about for that one in particular. I think that pretty much wraps everything up. So thank you for listening, and I hope you stay safe in these troubling times, I suppose.